G'day viewers. In this episode we're going to walk through the EGM Spreadsheet Calculator, which you can find on ResearchGate. The first thing I'll point out is that this spreadsheet calculator was constructed in 2017, and I'll just call that up here to show you. So you can see that it was created on Wednesday the 18th of October 2017. This means that the physical and mathematical constants which have been hard-coded into this document are from 2017, and some of these constants have changed slightly from then to now. Hence, minor computational output differences may exist between this spreadsheet calculator and our more accurate MathCAD solution algorithm, which you can also find on ResearchGate in PDF format. The computational output differences are trivial, but nonetheless they exist, and I wanted to mention it. For regular viewers of our channel, you will be very aware that we are completely transparent with every calculation and claim we make. We are not like the so-called whistleblowers you can find on the internet who never provide any verifiable technical information. By contrast, we encourage all viewers to scrutinise our calculations and conclusions. Okay, let's move on. As you can see, there are 4 tabs: the Summary tab, the Reactor Design tab, the Particle Physics tab, and the Cosmology tab. Each tab has been locked in order to avoid accidental deletions. You can unlock each tab by right mouse clicking and selecting Unprotect Sheet, and I'll just show you right now. See? Unprotect Sheet. Then you can make whatever changes you wish. If you make a complete mess, you can delete your local copy of the spreadsheet calculator and download a fresh copy from ResearchGate. The Particle Physics tab and Cosmology tab provides you with evidence that our primary equation, that's up here, which you can see on screen, is scientifically valid. We use the same equation in all of our calculations, validating the Bob Lazar story. The Summary tab has been broken up into 4 parts: Part A, Part B, Part C, and Part D. We also include a summary statement underneath Part D. Part A shows the big picture and establishes the scientific credibility of the EGM construct. On the left-hand side of the Part A region, that's over here, you'll see a list of 10 key scientifically validated achievements that the EGM construct generates utilising our primary equation appearing on screen. As I mentioned before, that's over here. The EGM construct unifies all scales of reality via the equation shown. That is, it unifies the scale of fundamental particles with cosmology. Please take the time to read all of the comments appearing on this tab. It'll be worth your while to do so. It contains a great deal of important information. On the far right hand side of the sheet, you'll see an image from the Bob Lazar website. This has been included to emphasise the origin of the 7.46 Hz gravity B wave frequency claim, which we have scientifically verified. Okay, let's move on to the Reactor Design tab. A lot of information appears on screen, and it's there for a reason, so please take the time to read everything you see, more than once if you need to. From a user perspective, you only need to interact with the blue cells containing white text. This sheet is broken up into 3 user input regions. We'll scroll down to the other 2 momentarily, but for now we'll look at the first region, where the user is required to specify an estimate for the mass density of element 115. The default value is 13.5 grams per centimetre cubed, but you can set it to anything you wish. The default value comes from the 2007 estimate derived by Burkhard Frick from the University of Kassel in Germany. I should also point out that the spreadsheet calculator assumes that a stable isotope exists at the Burkhard Frick mass density estimate. As you can see, if we change the mass density estimate from 13.5 grams per centimetre cubed to 12.63 grams per centimetre cubed, some of the results change. The results which do not change denote computational outputs which are independent of the mass density input. In other words, mass density doesn't affect them. Scrolling down, we see the remaining 2 user input regions. The upper input region allows users to modify the base diameter asserted by Ken Wright, whilst the lower input region allows users to experiment with the primary wedge height to base ratio. Both regions also allow users to experiment with disk thickness. So, just to reiterate, anywhere you see a blue cell with white texts, this is where users can experiment with their own estimates. Okay, let's now move on to the Particle Physics tab. Firstly, I'd like to repeat what I said previously. That is, please take the time to read all of the comments appearing on this tab. It'll be worth your while to do so. It contains a great deal of important information. I realise that the screen looks busy and there's a lot of information, but it's there for a reason, so please take the time to read everything you see. From a user perspective, you only need to interact with the blue cells containing white text. Before I launch into the operation of this sheet, I just want to point out that the predicted stable isotope, that's shown over here, is a 2017 estimate which does not take nuclear binding energy into account. This estimate has been surpassed by our 2023 predictions, which you can find on our YouTube channel. I've left the 2017 estimate here unaltered simply because this spreadsheet is an historical document and I wanted to preserve it as is. This tab is all about Bob Lazar's gravity A and B waves. I'll walk you through some of the results momentarily, but for now I need to mention that there are only 4 fields which the user should interact with, emphasised by the blue cells. The celestial location cell is a drop-down menu, and I'll show you that. See that? Drop-down menu. Okay. Whereby the user can select various objects in our solar system. The black hole solar mass cell allows the user to define the black hole mass, and the elevation cell allows the user to define their position above the surface of whatever celestial body they're considering. Finally, the target harmonic defines the overall solution. Now let's walk through some of the predictions generated by this sheet. The first thing I want to do is slightly move things on the screen a little bit so that we've got what we're interested in right in front of us. As I mentioned before, this sheet is pretty much all about gravity A and B waves. So here in this column here, the element 115 column, you can see I've got information about element 115 there, about a stable form of element 115, whatever that might be. I believe it's isotope 296. Hopefully that will be proven correct. But whatever it is, we can see that we have 11.44 gigahertz here as our gravity A wave frequency. Now that can't be changed. That's set in stone. That's a property of the actual element 115 atom itself, and nothing can change that. Okay. What we can change is what I showed earlier. So we've got a drop down menu here. We've got a list of different celestial bodies: Mercury, Venus, the Moon, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and the Sun. So we can put ourselves basically anywhere on the surface of those celestial bodies, and we can calculate what the gravity B wave frequency is going to be at the surface of those bodies, or at different altitudes. So let's say, for example, in the case of the Earth, at the surface of the Earth, we've computed a value of 7.44 Hertz. So this is very close to the 7.46 Hertz. I should also mention that in our MathCAD files, we have calculated 7.43 Hertz. So there is a very small difference between this spreadsheet and the more accurate MathCAD files. As I mentioned previously in the video, this solution was built in 2017 and physical and mathematical constants were different then, slightly, some of them. That makes a difference and therefore has shifted our answer slightly with the new constants and values, shifted it slightly lower to 7.43 as opposed to 7.44, which is what is appearing here. Now let's say, for example, that rather than the surface of the Earth, we're interested in what's going to happen, what the number is in low Earth orbit. So up here we've got Leo, that's low Earth orbit. So we can put in here 180,000 meters, and there you go. The gravity B wave frequency at 180 kilometers above the surface of the Earth is going to be, let's call it 7.2 Hertz. Okay, if we're interested in what's happening at mid-Earth orbit, that's MEO, we can punch in 2 million meters. Here we go. And at that altitude, at that elevation, the gravity B wave frequency is 5.2. If we're interested in high Earth orbit, so 35,780,000, okay, we can see that the gravity B wave frequency there is 0.6 hertz. So as I've mentioned many times before, what is particularly impressive about Bob Lazar's 7.46 hertz frequency value is that it is location specific, it is altitude specific. So it's inconceivable that Bob Lazar could have randomly selected a value of 7.46 hertz just out of the blue. It only applies to the surface of the Earth, it doesn't apply anywhere else. So I'm just going to set that back to 0 for the moment, simply because I like to sort of have a standard sheet when I work. Now here, black hole solar masses, I'm going to scroll over slightly to the right, and you can see that in this column, Schwarzschild, and these two columns, Schwarzschild black hole, what you're able to do is you're able to vary your black hole mass to whatever you like. So at the moment it's 10. The gravity B wave frequency just before the event horizon, 0.25 millimeters or something like this, just before the event horizon. The gravity B wave frequency is 1.4 megahertz. If you increase it to, say, 100 solar masses, that actually reduces. Now it's 1.43 by 10 to the 5 hertz. If you want to drop it down to 1, it's now 1.44, say, by 10 to the 7 hertz. You can calculate what the gravity B wave frequency is going to be in various black hole situations. This is, I must emphasize, this is for a Schwarzschild black hole, so it's the simplest example. And on the right hand side here you've got some more information about element 115. Now if we scroll down, you'll see that there's also a poster that I produced, I think it was 2005, where I've predicted a number of fundamental particles which have yet to be discovered, and I've actually been able to demonstrate over here that you can actually arrange all fundamental particles in terms of an harmonic periodic table. So if you know their mass and size, you can arrange that into a periodic table harmonically. So if you know its mass, you can predict its size. If you know its harmonic, etc., so on and so forth, and you can flip around, in between that, from what you do know to what you don't know, etc. I forgot to mention, you can also modify the number of harmonics. So if, for example, you wanted to target the 1001 harmonic, right, there you go, the numbers change accordingly, right? 415 is the optimal value. You've got to remember, if you've been watching this channel regularly, you'll know that if you try and move significantly too far away from 415, if you target a higher harmonic, the amount of energy that you've actually got to put into the solution skyrockets. So 415 is really the optimal harmonic, and you can see down here that's the gravitational reduction that you can expect. So if we put, say, 41,001 harmonic, remember the harmonics need to be odd, you can see you get 99.999% reduction in the value of gravity, but that comes at an astonishingly huge cost. So here, for example, is your power amplification factor that you'd need in order to achieve a 99.999% reduction in gravity at the surface of the Earth. Going back to what we had before, the default value, which is 415, you can see that you've only got 1.8 million compared to 173 trillion. So the power that you need to put in to target a higher harmonic is enormous. You achieve a very, very small incremental gain. So it really is a situation of diminishing returns, and you don't want to get into that if you don't have to. So 415 is the optimal harmonic. That's for any gravitational situation. Doesn't matter if it's the surface of the Earth or anywhere else. That's because this solution, our gravity B wave solution, is constructed from what we have called our unit harmonic operator, and you can learn about that by watching the videos on our channel. So anyway, that's the optimal value. So you can play around with 4 areas, 4 cells. This one here, drop down, your black hole solar masses, your elevation, and your target harmonic. And my advice is just to leave the target harmonic where it is at 415 and play around with these other 3 cells. And please take a very good look at the information that's on the screen. There are a lot of Easter eggs all over the place here that I've put in there. So please take the time, have a look. It's worthwhile. Move things around, slide things across, etc. Don't be fearful of making any changes or anything like that. If you completely destroy the spreadsheet, not a problem. Just you can always just download a fresh copy. But let's now take a look at the Cosmology tab. Once again, I'll start off by asking all viewers to please carefully read the content on this sheet. Okay, now that you've done this, we can move on. Of course, the blue cells with white text denote user inputs. In the About box, you'll see that 4 calculators are listed. This table refers to the number of calculators requiring user input. A 5th calculator is also included, but it is an output-only calculator, hence does not appear in the list. Calculator 1 achieves 2 objectives. Firstly, it relates the power spectrum Hubble constant to the cosmic microwave background radiation. Secondly, it relates cosmical age to the cosmic microwave background radiation and the power spectrum Hubble constant. The default user input values for Calculator 1 come from the particle data group. Please note that some of the output appears in red text. This has been done to emphasize significance. Calculator 2 relates Milky Way galactic structure, that is, its radius and mass, to the power spectrum Hubble constant, cosmological age, and cosmic microwave background radiation. The default radial input comes from the particle data group and denotes the distance from our solar system to the galactic centre. The default mass input guesstimate comes from McMaster University and Queen's University in Canada and is expressed in terms of Milky Way solar masses. Once again, significant output is emphasised by red text. Calculator 3 is a bit of fun. Users can input the beginning of a cosmological year and then their birthday. The output returned is the value of the power spectrum Hubble constant and the temperature of the universe on the user's birthday. Calculator 4 is basically a more convenient form of Calculator 1 when considering young cosmological ages. The default input value has been set to the age of the universe when water could liquefy thereafter. Calculator 5 is a summary of the predictions made by the EGM construct regarding important cosmological parameters. Please note that we derive all standard model of cosmology values, but we also predict a major revision of the dark energy density parameter downwards from 68% to 50% at some point in the distant future. Lastly, please take the time to scroll down and inspect the graphs we have compiled. You should find them quite interesting. Well, that's enough from me. I hope you've enjoyed the tutorial. Cheers.